Hai and Assalamualaikum warahmatullahi wabarakatuh. Our group will present about the case study of buckling of column in a structural frame.
Okay, so here is our group members. So we have three group members. The first one is Muhammad Hasib bin Ahmad Sani. The number matrix is AD230015. And then we have Mujahid bin Yusri. The number matrix is AD230049. And also the last one is Muhammad Shafiq Muhammad Atman. That is the number matrix DD230045.
For the next one, I'm gonna to present you about the introduction and objective. For the introduction, sudden sideways bending of the column, and for second one is happen before the material breaks. And this project we study using the Euler buckling theory. The importance of this project to ensure the safety in the structure like bridge, building and tower. For the objective, it's for analyze buckling of column. Second one, calculate the critical load. Third one is study the effect of the length, cross section and support. For the last, we practical solution to prevent the buckling. Next, the literature review. The factor of affecting buckling is was four things. The first one is boundary condition. For the second one is column shape and length. For the third one is slenderness ratio, and the last one is real world imperfection. There was two example for the failure, as you can see, and this is our formula that we use to solving our problem. So the formula is PCR equal to pi square EI divided by KL power of 2.
Okay, hi. My name is Muhammad Shafiq Muhammad Atman, and I would like to present about the problem definition for this project. So this project examines W6 multiplied by 50 steel column with a length of 7.32 meters, which is fixed at both ends. The column is braced to prevent buckling along its weak Y axis, but is free to buckle along its round X axis. So the study aims to calculate the critical buckling load in both directions and determine which axis will fall first. So the key challenge is to assess whether buckling occurs before the column reaches its material yield strength and which axis governs the failures. So that's all.
So we move to the next part, which is mathematical modeling. So as you can see here, this is the diagram for our problem definition. So the first one is the full diagram, the second one is the x-axis buckling, and the third one is y-axis buckling. So the mathematical modeling follows Euler's theory for column buckling. So next diagram is the calculation that we made, which is we use PCR equal to pi squared EI over KL squared. That's how to find the critical load for each axis. So we need to find for the x-axis and y-axis. Next, we use formula sigma CR equal to PCRY over A. So this formula are used to find the stress for the critical load. So as you can see here, we get the stress is 409.8 megapascal, which is lower then the yield stress. So we can assume that the buckling occurs before yielding. Next, the result. So from our calculation that we made, we can see that the critical buckling load for the column is governed by the y-axis, which has the smaller moment of inertia and shorter effective length. So the calculation that we made, we can see that the critical load along this axis is approximately about 1170.6 kilonewton. So in comparison, the x-axis provide a higher buckling load of 1785.6 kilonewton. Okay, next, the stress. The compressive stress induced in the column due to this critical load is 409.8 megapascal. So the stress is below the yield strength of 413.7 megapascal. So this can confirm that the column will buckle before yielding. This also verifies that elastic buckling governs the design and highlights the importance of accounting for geometric and boundary condition in stability analysis. So next, we also calculate the slenderness using formula KL over R. So we can see that the higher slenderness ratio in the y direction further confirm its greater vulnerability to buckling. So we can see that the y, the slenderness ratio for y is higher than the x. So these findings reinforce the need for accurate assessment of support conditions and cross-sectional geometry in structural design. So we move to the discussion part. So here we divide it to 4 parts, which is main challenge, improvement, principle and application. So from our project, the main challenge in this analysis was figuring out the main axis of buckling due to different moments of inertia and effective length. So that is our main challenge. So from our study, the improvement that we think we can make is to improve accuracy, more detailed method like finite element analysis, FEA, could simulate imperfections, lateral torsional buckling, and end fixity. So that's for the improvement. Next part is principle. So for the case study, using Euler formula, assume perfect material conditions and ideal end restraint. This may not reflect real-world imperfections and boundary flexibility. This assumption also can lead to overestimating the column's true capacity. So lastly, the application. So the principle that we use, shown in this case, have wider application in designing high-rise building, towers and bridges. So where slender structural member often face axial loads and can buckle. So that's all for the discussion. We move to the next part, which is conclusion.
Okay, for the last part for this slide, I would like to present about the conclusion for this project. This project applies solid mechanics 2 principle to study buckling in a structure frame. Using Euler theories, the critical buckling load was calculated at around 1170.6 kilonewtons. The analysis show the buckling occurs along the y-axis due to its smaller moments of inertia and higher slenderness ratio. So the result confirmed that elastic buckling happens before the material yields. These findings highlight the importance of proper bracing, reducing column lengths, and selecting suitable cross-section for safer and more efficient structural design in buildings, towers, and also bridge. So that's all from my parts.